Your German luxury car is hiding a secret that is killing your driving experience. Even if your suspension looks perfect, microscopic fatigue in your hydro-bushings is robbing you of that factory-fresh feel. We are revealing the 100,000-mile habit that masters the Autobahn, the systematic discipline that keeps a chassis rock solid at any speed, under any condition. The systematic discipline that keeps a chassis rock solid at any speed, under any condition. This is what a German performance sedan feels like at 160,000 kilometers from the factory, planted, precise, every input from your hands translating directly into trajectory, no delay, no float, no noise bleed through the floor. Planted, precise, every input from your hands translating directly into trajectory. No delay, no float, no noise bleed through the floor. Now let me show you what that same car typically feels like at the same speed after 160,000 kilometers on public roads. Without the systematic maintenance routine we are discussing today. Notice the difference. That is not age. That is not wear and tear as a concept. That is a specific, measurable, preventable mechanical degradation, and it has a name. German manufacturers build multi-link and double wishbone suspension systems to tolerances measured in fractions of a millimeter. BMW's M-Technik chassis, Mercedes's 4-matic front-end geometry, Audi's Quattro suspension mounting points. All of these systems function within a precision band that is essentially a closed system. Every component is calibrated to every other component. The problem with closed systems is that they fail gradually, not catastrophically. There is no single moment where the suspension breaks. Instead, there is a slow-motion sequence of micro-degradations that individually feel like nothing, but compound over time into a car that no longer drives the way it was engineered to drive. Engineers at the original equipment level know this. This is not a secret withheld from the public. The factory service documentation for most German platforms from BMW, Audi, and Mercedes-Benz include recommended replacement intervals for critical elastomer components. The problem is that most independent mechanics in markets outside Germany treat these as optional guidelines rather than precision maintenance milestones. There is a concept in German automotive culture that does not translate cleanly into other languages. Verschleißteile. It means wearing parts. Components that are engineered to wear at a known rate over a known distance and to be replaced on schedule, not when they fail. On schedule. Hydro-bushings and control arm assemblies are Verschleißteile. They are precision components with a service life. And the 100,000-mile threshold, or more precisely, 160,000 kilometers, is the outer edge of that service life under normal driving conditions. The most dangerous part of this decline. Drivers adapt to it. They unconsciously compensate for steering numbness, mild vibration, and reduced feedback without realizing the car has drifted far from its factory specification. We call this the slow creep. The degradation happens at a rate too gradual for a human nervous system to flag as an event. You drove the car yesterday. You drive it today. It feels essentially the same. But compare it to where it was 40,000 kilometers ago, or compare it to a freshly serviced example of the same model, and the difference is immediately apparent. The goal of today's video is to make that slow creep visible, quantifiable, and most importantly, reversible. Let us talk about hydro-bushings specifically, because this is the component most often overlooked in general suspension maintenance. And it is the one that has the most disproportionate impact on high-speed stability and steering precision. A standard rubber bushing does one job. It allows a small, controlled range of movement between two rigid metal components while absorbing vibration. Rubber is compliant, it damps oscillation, and it isolates the chassis from road inputs. In a conventional bushing, the rubber itself is doing all the work. A hydro bushing is fundamentally different. It uses a sealed internal chamber filled with a silicone-based fluid, typically ethylene glycol blended with a viscosity modifier to create hydraulic dampening. When the bushing deflects under load, the fluid transfers between internal chambers through a calibrated orifice. That transfer rate determines the stiffness characteristic of the mount. What this means in practice is that a hydro bushing provides tunable, frequency-dependent stiffness. At low frequencies parking lot maneuvers, gentle cornering the bushing is relatively compliant, absorbing inputs and keeping the ride comfortable. At high frequencies, motorway expansion joints, high-speed lane changes, braking events, the hydraulic circuit stiffens, maintaining geometry, and delivering the precision steering feel that German platforms are known for. This is how BMW achieves that paradox of a car that is simultaneously comfortable over cobblestones and razor-precise at 200 km/h. The hydro-bushing is doing the mechanical translation between those two modes. Now here is where the problem begins. The sealed fluid chamber inside a hydro-bushing is not eternal, over time accelerated by heat cycling, UV exposure, and mechanical stress. The elastomer housing develops microscopic fissures. These are not visible to the naked eye during a standard visual inspection. A mechanic looking at this bushing on a standard lift check will see a bushing that looks intact. No cracking, no separation, no obvious deformation. But inside, the fluid is migrating. Slowly, over thousands of kilometers of thermal cycles, the internal chamber loses its hydraulic integrity. The calibrated orifice that controls fluid transfer becomes less relevant because there is less fluid left to transfer. The frequency-dependent stiffness characteristic begins to collapse. The bushing starts behaving like a conventional rubber unit, compliant at all frequencies, offering no hydraulic stiffening when you need it most. We can quantify this. A new hydro bushing tested under a static load of 2,000 newtons will deflect by approximately 0.8 to 1.2 millimeters. A hydro bushing at 160,000 kilometers with fluid migration will deflect by 2.5 to 3.5 millimeters under the same load, sometimes more. That additional millimeter and a half of compliance does not sound significant until you understand what it represents geometrically. That movement translates directly into toe angle variation under braking and cornering loads. In a multi-link suspension, the toe angle of the rear wheels under load is what determines whether the car feels stable and planted or vague and nervous. A deflection of 1.5 millimeters at the bushing can represent a toe variation of 0.3 to 0.5 degrees, well outside the factory alignment specification of plus or minus 0.1 degrees. The visual inspection that mechanics rely on cannot detect fluid loss. The bushing looks fine. The geometry is quietly failing. This is the gap between a standard service and the systematic approach. The comparison between a depleted bushing and a new unit is immediate when you perform a physical squeeze test. A new hydro bushing resists compression with two-stage feel. A depleted unit compresses uniformly, offering no hydraulic backstop. The difference in your hand is the difference your chassis feels at speed. Let us follow the physics of what happens when one bushing in a front-end assembly begins to allow excess deflection, because it is not a single component failure, it is a cascade. The front control arm on a typical BMW or Mercedes-Benz multi-link system is mounted to the subframe at 2 points, a thrust arm bushing at the front and a main pivot bushing at the rear. Between those two mounts sits the wheel carrier, attached via a ball joint at the outer end. The entire geometry camber, caster toe is a product of these mounting points. When the thrust arm bushing degrades and allows 1.5 millimeters of additional deflection under braking, it changes the instantaneous load path through the entire arm. Forces that were being distributed evenly across the bushing mount are now being absorbed unevenly, with a higher proportion going directly into the ball joint. Ball joints on German platforms are rated for specific load cycles within a defined geometry envelope. They are not designed to absorb lateral forces from a compromised bushing. The result is accelerated wear at the ball joint taper, which introduces play, steering wander, and eventually, a clunk over sharp inputs. That clunk is the sound most mechanics use as their service trigger. But the ball joint damage was already underway tens of thousands of kilometers earlier, initiated by a bushing that looked fine. The second casualty in this cascade is the steering rack. Virtually every German luxury sedan and estate from 2015 onwards uses electric power steering calibrated for specific feedback. The system uses torque sensing at the column to modulate power assist. When bushing degradation introduces compliance, the steering rack receives noise in the signal. The torque sensor is interpreting false feedback from the compliant mounts and adjusting assist levels accordingly. This is why high-mileage cars have overly light steering. The driver experiences this as steering that feels connected but somehow numb, precise but somehow not communicating. The car turns, but you cannot feel it thinking. This is the tramlining effect. The vehicle begins following road grooves and crosswind gradients rather than driver steering inputs because the geometry is influenced by road forces. When you pull these components and examine them on the bench, the forensic story is clear. The thrust arm bushings show internal vulcanization cracking visible only with outer sleeve removed. The ball joint boots show micro-cracking at the base. The inner CV joint boots on all-wheel drive models show asymmetric wear from wheel carrier operating outside envelope. None of these parts look broken, they look worn, and worn, in the German engineering philosophy, means it is time. Now we get to the strategy, and the most important word is systematic because it is not about replacing one component, it is about restoring harmonic coherence. It is about restoring the harmonic coherence of the entire front-end assembly simultaneously. If you replace only one part, you introduce a mismatch. The new bushings have full hydraulic compliance, the rest are still degraded. The suspension geometry is now asymmetrically compliant. Handling inconsistency. The professional approach is to treat the 160,000-kilometer interval as a chassis reset. Everything that has an elastomer interface comes out together and goes back in new. This includes the front thrust arms with hydro bushings, the lower control arms, the front anti-roll bar bushings and drop links, front strut top mounts, and tie rod ends. For the rear axle on multi-link platforms, add the rear integral links, the trailing arm mounts, and the rear subframe interface bushings to the list. This sounds like a large scope, but it is far less work and less expensive than addressing secondary damage to racks and bearings from running components past service life. The most efficient way is with complete pre-pressed control arm assemblies from OEM-grade suppliers like Lemforder, Mila HD, and Phoebe Bilstein, already pressed in at factory spec. This is critical. Pressing in the field, without proper hydraulic press and OEM mandrel dimensions, risks distorting the sleeve and compromising the hydraulic chamber before it turns a wheel. Pre-pressed units eliminate that variable. The press-in geometry is correct because it was done on dedicated tooling. You are installing a system, not assembling one. Do not press hydro bushings in the field without OEM tooling. Incorrect geometry collapses the internal fluid chamber and converts your hydro bushing into a standard rubber unit. Individual replacement is viable if done on a press with correct OEM mandrel. This information is in the factory manual and is not optional guidance, it is the engineering requirement. One more thing. A complete front-end refresh without a four-wheel alignment is an unfinished job. New components have geometry slightly different from the worn ones they replaced. The alignment must be set fresh to factory baseline at normal operating height with the suspension loaded. Adjust at all four corners for E-Class, 5 Series, and Audi Quattro models. This is the same car, same engine, same wheels, same road. But the chassis is now operating within its original design envelope for the first time in tens of thousands of kilometers. The transformation in steering feedback is immediate and specific. Where there was a half second of compliance, there is now immediacy. The wheel communicates road texture. The return to center force that felt artificially assisted is now organic, the product of caster geometry, doing its job without compliance, robbing it of authority. On a chassis dynamometer, lateral response time improves by 15 to 25 milliseconds on a freshly refreshed front end. In the continuous feedback loop, it feels like it reads your mind. It is the difference between a car that feels like it reads your mind and a car that feels like it is lagging behind your intention. Braking stability improves measurably as well. Deviation drops from typically 0.8 meters to 0.15 meters after reset, within factory specification and consistent with a new vehicle. Financial case is equally clear. A car running outside geometry spec wears tires asymmetrically. Inside edge accelerates in wear. Asymmetric wear can cut tire life by 40%. Significant cost penalty. Correct geometry means even wear means full tire life, means money staying in your pocket rather than going to a tire fitter every 18 months instead of every 30. Financial decision. The cost of the refresh is typically recovered within 2 tire replacement cycles through extended tire life alone, before accounting for prevented secondary component damage. Practical field test time. Find a long, smooth, straight section of road, accelerate to motorway speed, and release the steering wheel briefly. A car with degraded geometry will immediately begin to drift toward road camber. Test 2. At 80 km/h, apply moderate sudden input and straighten. Count oscillations. Good integrity settles in 1 oscillation. Degraded bushings oscillate 3 times. Hydraulic damping loss. The Germans engineered these cars to be maintained precisely. There is a version of your car in your driveway right now that is significantly better than the one you drove today. Distance is a reset. Every kilometer past 160,000 without this refresh is a kilometer of secondary damage accumulating in components that cost substantially more to replace than bushings. Restoration service. Drop your platform and mileage in the comments. Tell us what before and after felt like. If your car is past 100,000 miles, this was for you. Like, subscribe, and see you next time.